So hi, and welcome to this IMechE webinar. My name is John Meyer. I'm the Chief Product Officer at AP Works. We're a business that's a spin-out of Airbus, who you probably have heard of, and we specialize in additive manufacturing, specifically in how can we use additive manufacturing to develop better products, because we believe this technology is changing the face of manufacturing. So today I'm here to talk to you a little bit about the technical economics of additive manufacturing, and I hope I can gain some of your interest in the technology and encourage a few more of you, if you haven't already done so, to get online and find out more and work on your continuous professional development through looking at this emerging technology. So, on to the next slide. So first of all, what is additive manufacturing? Now, you might have heard of it under many different names, including most commonly 3D printing is probably the most common term used, but there are many others. And actually, it covers a very wide range of technologies. So just to walk you through them, the first technology, and the one I'm going to talk about mainly today, is powder bed fusion. This is essentially where you're building layer by layer, spreading powder within a machine and then using a laser which is steered around to melt the material to make a solid part. The second type of additive manufacturing technology, which you might be familiar with as stereolithography, is technically called wrapped photopolymerization. Now, this is again using a laser, but generally speaking, it's a much lower powered laser. So you're talking milliwatts of power. And that laser is just there to trigger a chemical reaction in a resin bath. Again, it's steered to create the three-dimensional shape, but the energy you're putting in is not melting material, it's simply triggering a photopolymer reaction. The third one, material extrusion, is possibly the one you'd be most familiar with. This is the classic 3D printer technology that you might be able to have on your desktop. Perhaps you've got one in your office or even at home. And this technology works by extruding normally a polymer material through a nozzle, through a hot nozzle, and then moving that nozzle around to build up the three-dimensional shape. The next technology is material jetting. Material jetting, as it describes, I suppose the material is jetted. Essentially what this looks like is a bit like how a printer cartridge works in terms of jetting inks, except in this case you're jetting a polymer material which is then triggered to cure via a UV light source that's normally following just behind the printer head. So this technology can be very fast. You can also mix materials, colors, so it's quite interesting for prototypes, desk prototypes. You can get to really interesting results using those technologies. The next technology family is binder jetting. Binder jetting, a little bit like material jetting, you use something akin to a print head, but instead of jetting the material itself, it's simply jetting a binder or a glue, effectively. And you're actually spreading a powder material on a bed, a little bit like powder bed fusion, but instead of melting that powder, you're locally bonding it together using this selective deposition of a binder. And of course, that will give you different properties and results than a fusion-based process. The next technology, actually, if you saw it, you would probably think it looked exactly like welding or cladding, if you're familiar with those technologies. Directed energy deposition. Essentially, the difference here is you're providing an energy source which is moving around, normally a laser beam or an electron beam, which is creating a molten puddle of material. And then you're pushing into that molten puddle either a wire, as you would with a classic welding process, so stick welding, or you're spraying a powder in to that melt pool. And by moving that energy source and that material around, you're able to selectively build up a part. Typically with those technologies, you're looking at a lower resolution than the other technologies. So normally the things look pretty lumpy and bumpy, and the goal is generally to then finish machine the parts. So it's a lot about efficiency of material consumption with those technologies. And then last but not least, sheet lamination. Sheet lamination is one of the older techniques used for additive manufacturing. Essentially, the simplest version of this is taking pieces of paper, laminating them together and selectively cutting the contour of those so that at the end you have a bonded paper block and a bunch of scrap that you throw away around the edges. More recently, people have worked on this with foils and different types of materials, and that's where it gets more interesting. Things like printing special capacitors, electronics, and so on. So it's come a long way since the early days of paper binding. So, I mean, the main message here is that it's a wide range of technologies. The main thing they've got in common is that they're all adding material to build up the shape of the part rather than removing material from a pre-existing lump of material, which might be the case, for example, with machining of a billet of metal. And that they all use CAD data as their key input to describe the shape. So they don't require special form tooling. And that's one of the big advantages of additive manufacturing in general, is the fact that you're going from data to manufacture without an intermediate step of producing a bunch of tools. Today we're mainly going to talk about powder bed fusion and mainly laser powder bed fusion. Little image on the left is a nice snapshot that gives you an idea of what it looks like in the machine. This laser is zipping around at very high speed, and you can see the little sparks coming off where the material is being melted, and there are small ejections of material from the melt pool. This is a view on one layer, so that's powder you can see, and a bunch of cross sections that are being melted by the laser. On the right, you should see a video, and this is just showing what you get at the end. So this is a big block of powder that's being removed from the machine. The parts are mounted on a build platform, so they're actually built up off a piece of metal that's in the machine, the build platform. That's then removing the build platform with the part on top, and then it has to go in a furnace. So it's quite important to realize that with this type of technology, because you're melting and fusing material, there are residual stresses as a result of the process, and so we have to perform a post-process heat treatment. And in general, there are quite a few post-processing steps required: heat treatment, removal of supporting structures, which are there to minimize the distortion that occurs during the process. So it's not a trivial process to set up, but it doesn't require physical tooling. So bearing that in mind, I wanted to give you a little overview of what the key motivators for additive manufacturing adoption are. So why are people using the technology, essentially? And as usual in life, there's no simple answer. Everyone is using this for different reasons. And sometimes the reason one person is using it could actually be a detrimental factor as far as another person is concerned. But I'm going to do my best to give a very brief overview of what those motivators might be. So one main motivator, and this is where additive manufacturing started out, is all around how much does it cost you and how much time does it take to get to a first part. Now, originally, additive manufacturing was being used purely for desktop prototypes which were non-functional. They were just shapes which could show someone what something was going to look like when it was produced. The materials didn't have the properties necessary for them to be functional. Now, the technology has come an awful long way. Nowadays, people are using the technology, particularly with metals, for real functional prototyping and rapid development. And that goes as far as things like rocket propulsion systems. If you're interested, I suggest Googling or use any search engine you like to search for some of the propulsion systems that have been produced with additive manufacturing. Another area is motorsport, and there are many, many parts nowadays on racing cars which are produced by additive manufacturing because it enables a very rapid design iteration. You can change the design and have the parts on your desk next week, and they're functional. They're able to perform a serious role in the product. And that is one fundamental way in which additive manufacturing is actually changing the way we do things. It enables you to do more functional testing of your products rather than just virtual testing and analysis. And that can actually take away some of the grey areas. Any one of you who's worked with things like CFD or FEA will be aware that generally you need then a physical test to validate what you've done. And the ability to do more iterations of physical tests and to capture some of those grey areas which those simulation methods are not brilliant at capturing is a real advantage to be able to do a physical test. And also to, at low cost, produce several variants of the same thing with slight parameter changes in the design, so that you can check whether your actual optimum was slightly off where the software said in the design phase, because it couldn't quite capture all the variables accurately, or some of your inputs were not quite representing reality. The next way that many people are using additive manufacturing is for more optimized and integrated design solutions. So when you take it really seriously that this is a technology for production, and generally speaking, today it's only viable for short series production or low volume production, we're talking hundreds of parts, maybe in some extreme cases, tens of thousands of parts, but generally speaking, it's at the low volume end. But if you decide that that technology is what you want to work with, then of course you can design for the process. And there are many, many design freedoms that additive manufacturing offers, which are not possible, at least not easily, with other manufacturing approaches. So generally, you could take a part which may be an assembly of tens of small formed, brazed, assembled parts and integrate them into a single part. Of course, casting can also do that within certain limits. Where additive manufacturing has a big advantage is you can go down to much smaller wall thicknesses than you can with casting technologies. And of course, you haven't got that extra cost of the tooling, even with rapid tooling, that you have with the casting approach. To give you an idea of the sort of wall thicknesses that you can go down to, it's not uncommon to be able to go down to, say, 0.2 millimeters wall thickness in materials like titanium alloys, nickel superalloys. Those materials are extremely difficult to form. They're extremely difficult to machine. So the ability to produce at that length scale in those fine features is obviously a design opportunity that doesn't traditionally exist. And it's mainly been exploited today in things like heat exchangers, also in aerostructures and propulsion systems. So the rocket motor propulsion, also aero engine propulsion. There's the famous GE example of an injector nozzle on the LEAP engine, which is produced using this technology, and they've done a great job of exploiting the design freedom. And then the other area where it's used is mass customization. And this is really about the fact that the process, because there's no tooling, the process doesn't really care if you're producing 100 of exactly the same part or 100 parts which are subtly different, which are personalized. There's not, in terms of manufacturing, there's not a cost impact of making that personalization. Of course, there is an impact in the design phase, and so the people who are exploiting this effectively have focused very heavily on the digital chain, so how to capture the customer requirements in terms of customization and automate the flow of that data all the way through to data for manufacturing process that drives the process. As soon as you have a human having to get involved at some step in that chain, the costs can become prohibitive for mass customization. The interesting places that's been applied, which you may or may not be aware of, so fashion goods, there are quite a few companies producing things like glasses frames, which are customized to the user. So they're scanning the face, they're adjusting the geometry to get the lenses exactly the right place, and they're putting all of the value into the frame rather than the lens. You also have things like medical implants and also tooling fixtures for surgery, which are customized to the patient. So produced using, for example, CT scan data of the patient, and then having this workflow, which is able to then design in a very automated fashion the specific fixtures or implants that are needed to minimize the amount of designer effort that's required. And essentially the role of the designer in this world changes from one of designing parts to one of designing processes that design parts. I think that's quite an interesting trend for engineers to follow and think about how that affects our lives in the future. And the other one, of course, so prosthetics links into this medical implants. It's obviously things like prosthetic legs, prosthetic hands. You might have seen some of this in the media. Again, a great opportunity for mass customization to change people's lives, and I think that's a wonderful thing. So I've just got a little video here for you to show one team we worked with and how they use the technology.
3D printing or additive manufacturing has a lot of value for us, and so that's why Airbus started to help us on this.
We have already started with two parts. One for the system to control the wing, and the other part is to assemble parts of the radar.
You can print in many materials today. You basically start with a powder volume of that material, and by layers with using laser beams, they melt by layers, little by little, to end up with the part. We use 3D printing first because we can do many parts that would take way more time to machine.
Main benefits will be the weight. Weight is a key parameter for such a highly competitive boat, but you have also cost and lead time, which will play a role. In fact, you can use many different material. We are using scalm alloy, which combines the light of the aluminum and almost the specific strengths of the titanium. It brings opportunity for new shape and very complex parts.
For a piece like this, you have to imagine how complex it can be if it was made out of one single bill of material. Instead, by 3D printing, you don't have to machine all that parts. There is a lot of weight saving and time saving too. The limitation is only your brain and your thinking.
Okay, so hopefully that gave you an idea of at least one perspective on why additive manufacturing can be interesting and can be applied to solve engineering problems. And of course, there are many different types of engineering problems. It's only one example. I thought in this case, a way to show some of the economics of additive manufacturing and some of the things that make it unique, I would introduce a case study for you, which is a sort of theoretical case study, but hopefully will give you a nice overview of when additive manufacturing can make sense. So the first topic I wanted to mention in this context is why design for additive manufacturing is different and why it's important to understand that if you want to exploit the technology fully. Obviously, all manufacturing processes have limitations and capabilities, and we know that as engineers, if you're going to design something, you really have to have a mental model of how it's going to be produced if you want to do, let's say, to produce an optimum design. Now, design for AM is important, it's different, mainly because part cost, in this case, has a very high sensitivity to the part mass, and to some extent to the bounding box volume of the part, but very high sensitivity to part mass. Now, that's not necessarily the case for many other processes, where in fact the part mass itself, it may be that a lighter part is typically much more expensive because you're having to apply much more machining, for example, to remove material, and the geometry is becoming more complex, and therefore you have more machining operations. In this case, we have a very low sensitivity to the geometric complexity. So if you make the part more complex in order to reduce the amount of mass in the part, actually the part will get cheaper. And that's quite interesting because it's really contrary to our initial perception. If we looked at two parts on the table and you asked yourself the value of them, you would always assume that the one that was more complex was of higher value and higher cost. And actually, in this case, it's the contrary. A simple additive manufactured part will often cost more than a more complex one, partly because of this link to volume, but partly also because we're extremely sensitive in this process to certain types of geometry. We have to really take account of design rules. So you can produce things that look very, very complex and almost impossible to produce by other means. But don't allow yourself to be fooled into thinking that just because you can do that very crazy, complex design, that means you can do anything. This is the sort of misconception of additive manufacturing. You can do certain things that are really, really difficult to do in other ways, if not impossible. But there are some things that look very, very simple. Traditionally, we would think that's easy. You know, it's a block. We just machine it, done. And by additive manufacturing, that can be extremely difficult to produce because of thermal stresses in the process, because of the support structures needed. So if you take a traditional design and you simply go to someone and say, please produce this by additive manufacturing, you will almost always be disappointed because it will almost always come out more expensive and you'll wonder why anyone is using it. The people who are using the technology effectively are designing for additive manufacturing. And then they're getting this dual benefit of cost benefit because the parts would be cheaper, but also potentially they can enhance the performance by exploiting this geometric complexity. That should always be the objective. And if mass matters to you, for example, as in aerospace, of course, it's a pretty nice sort of virtuous circle to have mass saving, driving cost saving. That's a really attractive proposition, which is sort of unexpected. So the hypothesis for this little case study is that increased raw material cost doesn't necessarily mean higher part cost. And the reason for that is that most of the costs of the process are driven by actually the time on the machine, which is about volume of part. It's not really about how expensive the material is. If you think about it, that should be relatively obvious. In the end, these processes use very little material. They use about the same amount of material as ends up in the final part. With some of the traditional processes we're more familiar with, like machining, we're wasting an awful lot of the raw material. So the raw material represents quite a big proportion of our cost in our bill of material. In this case, it's not the case. The raw material represents less than 10% of the cost of the part. So a high raw material cost does not necessarily mean a higher part cost, as long as you optimize to minimize mass. So if that raw material is more expensive because it has improved material properties, and you exploit those improved material properties through design to minimize the mass of the part, you can make not only a lighter part, but a cheaper part. And that's quite an interesting proposition. Now, some of you may be really zipping ahead here and saying, but hang on a second, you said low volume production. How can I afford to do optimization if I've only got a small volume of parts to amortize that over? Of course, the answer is in the past, it wasn't really feasible. But increasingly, we're seeing solutions for topology optimization which are more and more automated in terms of the downstream processing to generate a good design file, so a CAD model which you can really use. And that makes a huge, huge difference to how viable this is at lower volumes. So you're not talking about hundreds of design hours to do an optimization. You're maybe talking about a handful, a day or two at the most to do that. So here's my case study, which is, I chose a brake caliper just because this happened to be something where we had the loads data and we had the references. So the process we followed was to define a common set of functional requirements for the part. This is mainly around geometry, key interfaces, and loads. Our goal was to run a design optimization for 3 different materials. Now, if you're not familiar with these materials, the ALSI 10MG is a low-strength aluminium silicon alloy, and it's, by additive manufacturing terms, is a relatively low-cost alloy. In the middle, you have Ti6Al4V, that's titanium 6.4. This is it's a pretty high-performance titanium alloy. It's the workhorse of aerospace for titanium alloys. And to give you an idea, roughly the cost of the powder is 5 times the cost of the aluminium silicon 10 powder. And then Scalmalloy on the right, which you almost certainly won't have heard of unless you're really into AM already, is an alloy that we developed in AppWorks within Airbus. And this material is a scandium containing aluminium alloy and has very, very high specific properties. But unfortunately, scandium is very expensive as well. And so the cost of this alloy is slightly higher than titanium. So that's very, very high for an aluminium alloy. What we wanted to do was evaluate each of these scenarios. So we see, what do the designs look like, bearing in mind these all have different material properties, and what does the cost look like of production for each of these, and see then where do we end up? How critical is this design for AM, this optimization of the part? So very briefly, the process we followed was we had a fixed design space and loads and boundary conditions. Basically, the design space is where are we allowed to have materials, so taking into account areas where we would have clashes in a kinematic case, or where we need to have fixed geometry for assembly interfaces, for example. All of that is common. The loads and boundary conditions are common. And the only thing we varied were the material properties and the process characteristics, which then is enabling us to do two things. So on the left, we used a piece of software called Parameters. It's available online. It's a sort of pay-per-use solution for topology optimization, and it's pretty easy to set up. So we used this because it was easy to run 3 cases in not much time. We ran a topology optimization on this side and a finite element validation, and this gave us a design solution for each case. That design solution we then fed into IMechE, which is our cost estimation tool. You can access that online, it's free. And essentially this would give us an estimation of the cost of producing each of these solutions. And it takes into account not only the design geometry, obviously the material and process characteristics, but it does, through an algorithm, it optimizes the build orientation, it looks at how much support we're going to need to produce the part, and it looks at the processing parameters for the material, and then it calculates production cost based on raw material, processing, post-processing, NDI, and so on. And that gave us our two outputs, mass and cost. And when we started this exercise, I was just really curious to do this. And what enabled us to do it was having tools like this, which made it really easy. So we didn't have to invest lots and lots of labor hours in doing this kind of trade study. So if you'll prepare the drum roll, the results are on the next page. Now, what's interesting here is you can see the 3 solutions do actually look quite different. The titanium and scalmalloy solutions do not look dramatically different in terms of topology. There are some differences. The interesting thing with the aluminum silicon 10 one on the left is how much it runs into the edges of the space. You can see this sort of ghostly image is the design space that was available. And it's really following the edges of the space because the properties simply are not good enough to let's say, optimize and meet the stiffness constraints without running out and using all of that edge space. To give you an idea, the aluminum silicon 10 alloy has a yield strength in the range of around 220 megapascals. Titanium 6.4 has a yield strength in the range we use for this 900 megapascals. In reality, with additive manufacturing, it can be quite a bit higher. It could be well over 1,000. And then with scalmalloy, we use the yield strength of 450 megapascals. Again, that's sort of a basis level. So it's the typical properties are quite a bit higher. You can see that each solution came in with a similar margin of safety, which we built in to the optimization. So they're quite equivalent solutions. And the mass you can see reducing. And interestingly, the scalmalloy came with the lowest mass. That wasn't necessarily what we initially expected because titanium actually has slightly better specific material properties than scalmalloy. But of course, in any design, you have certain features, and you can see them in blue, certain features which you've got to have regardless of the stress constraints. So there are minimum wall thicknesses for things like the pistons, the cylinders for the pistons, and though, of course, the density of titanium is higher, so that's driving more mass into those areas which are, let's say, parasitic mass versus a lighter, lower density alloy which has the same features. So another way, so just to summarize the result there, you can see that the part mass of the baseline design, this was the design that we took for a milled solution, it's about 4.5 kilograms, and we're achieving quite substantial weight savings. I'm not saying that that baseline design was highly optimized. Typically, you'd expect a milled solution that was highly optimized to maybe be in the range of 2 to 2.5 kilograms for a similar problem. So that's maybe a little bit unfair, but let's put it in there somewhere. It's still a significant saving. Now, if we go for the optimization results with respect to cost, what's interesting here is that the lowest cost material by additive manufacturing is significantly more expensive than the highest cost raw material. Again, this is that virtuous circle effect of weight saving and cost saving. And of course, the interesting thing, how much more expensive that baseline design is to produce by additive manufacturing than to produce simply by milling. And for aluminium, this is probably the most exaggerated example, because aluminium is very, very cheap to machine and pretty expensive to produce by additive manufacturing by comparison. If you compared this with a nickel superalloy, in many cases, the additive manufacturing solution would be similar or cheaper than the milled solution because of the nature of the alloys. Same with titanium alloys, it would be closer. But the key point is once you go to an additive manufacturing solution, the costs are reducing dramatically as you optimize the design. And another way to look at this is a Pareto graph, which some of you might be familiar with, would be to plot those solutions against so recurring part cost versus part mass, and to look at how those data points stack up. And the interesting thing in this case is, generally speaking, if you sought to further optimize the milled aluminium baseline, you would get a series of points going diagonally up and to the left of where that point is for the milled aluminium baseline. Because generally, as you're saving mass, you're adding additional processing time, additional processing costs, machining setups, and so on. With additive manufacturing, the line is diagonal down and to the left from the baseline design in the top right. So as we're optimizing to save mass, we're actually approaching a better cost solution as well as a better mass solution. And hopefully that gets you thinking about how important it is to consider this at the start. If you don't consider the design optimization potential of the technology, and here I've only shown structural optimization for a static case, but in fact, of course, for flow problems where you're using CFD and so on, also similar optimizations are possible, which can minimize the cost of the solution as well as improving your performance metric. And I think if you don't do that, you'll often get the case where you say additive manufacturing is very expensive. And the point is you're not exploiting the main benefits of the technology, which are related to the design potential and the fact that you can get a better trade-off between cost and mass. So in conclusion, in additive manufacturing, mass is cost, or is at least very proportional to cost. And so you really need to think about that and about the design solution, not just simply taking an existing design and producing it by AM. That can work in some cases, particularly with very high value materials, where just the material saving is worth it. But in the vast majority of cases, you need to consider the design as a factor. One interesting point for those of you who are materials people is that it actually presents significant opportunities for new material development. You have completely new processing dynamics in each one of those additive manufacturing process families. You have a different chemistry, physics going on. In the example of powder bed fusion, you have very, very high cooling rates. That's what enabled us to develop scalmalloy, which is loaded with scandium to give a very high strength material. With traditional processes, if you added that much scandium, you would get defects rather than high strength. It's a different process, and therefore you're going to get different material properties. There are lots of opportunities, therefore, to develop new materials. And the beauty of this process is that the advantages of improved material performance can pay for themselves, because they can, generally speaking, reduce the costs of production as well if they're reducing the amount of material you need. And I think that's quite an exciting opportunity for material scientists who perhaps are getting a bit fed up with using the same old alloys that were developed back in the 50s. More expensive raw materials can result in lower cost parts. So we've shown in one example that we can achieve that. The key there is reducing the part mass or the part volume. If you can use those properties in order of that expensive material in order to sufficiently reduce the volume of the part, you will get a cheaper part as well. And then that's where the opportunity lies for new materials. And I hope I've hammered the message home, but optimization for minimum mass is really essential. It's not just optimization for minimum mass. The other factor is really around the design for the process, minimizing support structures, minimizing issues with powder removal and so on from the process. So I would recommend that if you're interested in what these technologies can do in your product area, the best thing to do is to find a business which you can work with who are experts in additive manufacturing. And there are quite a few businesses out there who are specializing in that, of course ourselves, but also others. And I think going it alone is not, it's a long road, and it's much better to work with people who have overcome those things and to find a way to collaborate to develop new solutions. So that's roughly it. A holistic approach is essential to achieve a best value design. I think I'm kind of repeating myself, but there you go. That we all do that sometimes. So hopefully that was interesting enough to prompt some questions. So I'm here to answer any questions you might have. Thank you very much.
Thank you, John, for the very interesting presentation. Very good overview. And I think we have a couple of questions from the attendees coming in already. So if you have any questions, please feel free to use the tool to log your questions, and we'll try and answer them as good as we can. We have a first question about the AM Expert tool that you mentioned, whether that is a free web-based service available to all, or how to access that.
Yes, I probably should have made that clear in the presentation. So it is a free web-based tool, and you can reach it at www.amexpert.de. So if you go there, if you click on the Get Instant Quote, effectively you can assess your geometry for free and get some cost information.
Good, thanks. We have another question about the material properties. And I guess that's something you mentioned briefly at the beginning in terms of post-processing heat treatment. There was a question about the limitations of the strength of the components of the material grain boundary level. How does the strength compare for a like-to-like forged versus AM component?
So that's a really good question. So it can be somewhat surprising to find out that actually with these processes, you can often achieve, in fact, better properties than forging and casting. Generally, it depends upon the alloy system. So you have a different process dynamic with powder bed fusion, which is what we're talking about here. You have very, very high cooling rates in the process. And that can be detrimental for some materials, but can be extremely beneficial for others. So the Scalmalloy example I gave is one where it's extremely beneficial. But even for, let's say, workhorse alloys like titanium 6-4, grade 5 titanium, which is frequently used in aerospace, oil and gas, marine, and so on, because of its corrosion resistance and high strength, the as-built properties, just with a stress relief heat treatment, are similar to a solution treated and aged forging, in fact slightly above those typical properties, which is somewhat surprising to people. And in fact, if you want to get the strength down and the ductility up more to the range of a standard grade 5, then there are heat treatments you can perform to do that. That being said, the solution treatment aged sort of properties are not bad in terms of ductility. You're still looking at 8 to 12% elongation at failure, but with UTS that's in the range of 1200 megapascals, which is extremely high for a titanium 6-4 material.
Okay, thank you. We've got a follow-up question on this, on how readily available are the tested material properties, i.e. how well known are they?
So that's a very good question, and one that pops up in the aerospace industry all the time. We discuss it frequently about how we can bring and pool that data. I'm pleased to say that there is some activity now in the US, at least on aluminium alloys, to create aluminium standards where we could put the data through MMPDS, which would mean that then they would be widely accessible to people. So that may solve the problem for aluminium alloys. There are now some standards for titanium alloys and Inconel, which is another material that is very easily processed using this technology. And the material data, I'd say, is not widely available, but increasingly we're putting that, we are putting that data out there. At least we're providing it to our customers readily. And I'm hoping that there'll be more transparency across the industry in the future, because a lot of testing has been done, but we just need to get it all statistically analyzed together rather than every company doing their own thing.
Okay, thank you. We've got a couple of more questions on mostly the fatigue properties. So a question, what are actually the FNDT properties, and are AM parts sensitive to fatigue loads, and how do AM materials tend to perform in fatigue due to layered fused construction? I guess you might want to answer all of these in one go.
I will try. So from a fatigue point of view, the most critical aspect is always the any surface defects, so surface condition. With additive manufactured parts in the as-built condition, the surface texture has lots of peaks and valleys. It's effectively an imprint of the powder bed. So obviously that is not great for fatigue, for crack initiation. So if we are producing parts for fatigue critical applications, we would either perform a chemical etching process to remove the surface region and get it smooth, or we would even machine, around critical features, you would tend to do local machining to guarantee the surface quality. And then you're performing fairly standard NDI, dye penetrant inspection, if necessary, X-ray or CT. Generally speaking, the defect that's going to cause you a problem is the surface breaking defect, so one that you can detect with dye penetrant testing. So you're really looking for a crack or a local pore that hasn't been cleaned up in post-processing. In terms of internal defects, the level of internal defects is actually pretty low compared to what you might expect from a casting, for example. One of the challenges we've had is that with non-destructive testing nowadays, we can see tiny defects, and so there's a lot more effort put into understanding them. But to give you an idea, that the sort of pore size that you might generate in the process if it's not running well would be of the order of 200 to 300 microns in diameter, which is not a huge pre-existing flaw. It would tend to be overwhelmed by any surface defect. Any slight scratch on the surface would tend to initiate a crack long before a subsurface defect of that size. I hope I've answered that.
Okay, thanks. Yeah, we actually have a couple of follow-up questions on this. One question about the confidence level that the part has been manufactured without inclusions, and whether traditional ultrasonic testing is performed to look for defects, or what other quality control techniques are used specifically for this.
Okay, so inclusions is an interesting one, because I guess it's an obvious question to ask when you deal with powders, where you have, a high potential for something to get mixed in there. In general, the let's say control of that is through very tight quality control, but it can happen even from the powder manufacturers that you could have an inclusion. Generally, we're looking when an inclusion might be critical, we're looking with X-ray or tomographic methods at the parts The reason being that the geometry is generally too complex to address with traditional ultrasound methods. You get too much reflection. There are some people working on some very smart methods, which I've seen recently for ultrasonic inspection of more complex parts. I'm looking forward to that being available, but at the moment we tend to use either X-ray or computed tomography.
Okay, good. Then we've got another follow-up question on the same lines. I'm trying to group the questions a little bit by technique.
Okay.
There was a question about powder bed fusion. Surface finish is an issue. What effect does this have on the propensity for fatigue crack initiation at the surface? And kind of a follow-up question whether shot peening can be used to harmonize the surface finish.
So the question on whether it's an issue, I think I mentioned it earlier, but it is, yes. So obviously the surface finish is the most critical factor to fatigue crack initiation. So it's very important that if you have a fatigue-driven part, that you address that. That's not to say the fatigue performance is unusable in that condition. I mean, it's just a question of what stress you can tolerate, for infinite life, and it's quite a bit lower with that surface finish than you can tolerate with a perfect milled surface finish. So you just need the appropriate SN curves. But it's very important to consider surface finish when you're doing design. Because obviously it's something that can be specified on the drawing. If you specify perfect surface finish everywhere, it'll be extremely expensive. So it's better to look at which regions are above a certain stress threshold and therefore need a special surface finish.
Okay, good. I think there was the question about shot peening. I'm not sure if you've answered that one.
No, I haven't. So the shot peening, that is used. I'd say for achieving a nice aesthetic surface finish, it works great. Frequently used sandblasting, shot peening, and so on to get an improved surface finish. Where you talk about safety critical parts, you need to be cautious that shot peening doesn't disguise a crack by folding material over and making it difficult to detect by a dye penetrant test. So generally, if you're then going to do a dye penetrant test, you need to ensure that you have a long enough etch to remove any material that may have folded and disguised a defect that was underneath. So that's just a consideration. But in general, for most functional parts, which are not fatigue critical, then it's a perfectly acceptable surface method.
Okay, we have one more question about the surface finish.
Okay.
Whether that varies with the choice for different materials.
Yes, it does. It depends on a couple of things. One is the material itself, and the other is the process parameters that are applied. So what the layer thickness of the process is. Generally speaking, they're somehow coupled. So alloys which require a lot of energy to melt and have low thermal conductivity, so think of things like titanium alloys, tend to have a better surface finish, things like steels as well and Inconels, than materials that have a very high thermal conductivity and proportionally speaking less energy required to melt, because they tend to have some, let's say, some bleeding or agglomeration of the melt pool, so you end up with powder particles being partially melted and stuck to the surface of what you're melting. With things like Inconel, titanium 6-4, the surface finish tends to be better because you get a much cleaner edge to the melt pool that you're producing. But of course, it also depends on things, let's say production choices. You can increase layer thickness and go faster while reducing resolution. That has a cost implication, but also a negative impact on the surface finish. So you do need to decide what you want and be careful when specifying to ensure you get a good value for money product.
Okay, good. We still have a couple of questions on the material side. And the next question would be whether there are any high temperature alloys available for additive manufacturing.
So I guess that depends on the definition of high temperature, but yes, I mean, there's some quite interesting, Inconel 718 and Inconel 625 are quite commonly used in additive manufacturing today. there have been some very interesting developments, for example, in GE Avio, which was acquired by GE, on titanium aluminides, which process very well using electron beam powder bed fusion, so a slightly different metal powder bed fusion process. And those alloys are very interesting. A lot of work has also been done in the UK on things like Hastelloy X. So there's a lot of work has been done on those materials. As always, it takes time for them to get through to say rotating part critical applications as opposed to static things like exhausts and so on, which they're already used extensively on.
Good, thank you. And we've got another question on the repeatability of the mechanical properties with AM. I think you answered that partially, but maybe you would just want to reinforce what you said there.
Yeah, so repeatability, as with any process, it depends a lot around the process that's applied. So if you're repeating the same process, you can qualify the material to an aerospace standard, so generating statistical, curves for static properties, and you can get, T99A basis values. You get a nice normal distribution, but that all depends on the process being run properly. Of course, if there are variables changing which are not being controlled, so for example, if you went to 10 different manufacturers and just asked for titanium 3D printed, you would probably get 10 different answers because they won't all be applying the same process. So as always, specification is very important in terms of process in order to get a consistent result.
Okay, good. And because we're obviously talking about aircraft here, we've got two questions about the certification. So one, how do airframers qualify new AM materials for certification for flight? And I think a very similar question, where does AM stand today in terms of certification regulations and being flight ready? What are the challenges and what work is ongoing to overcome these barriers?
So in terms of EASA and FAA basically said that the approach to be taken is the same as for any other special process where you need to qualify the materials used, qualify the process, validate material properties, generate allowables, and so on. And so that's the process that has been followed. There are qualified serial production applications of powder bed metal additive manufacturing in service today on civil aircraft. In fact, they've been applied on military products for quite a long time. So I'd say the status is pretty mature, but again, for a very particular scope today. So as always, if you want to expand that scope of materials or that scope of application, so today we're talking about non-safety critical parts, class 3 parts, then that's one hurdle to get over, which has been achieved. As we go into, let's say, primary structural elements and things like that, there'll be a lot more work needed to be done. And that's normal. That's with any new material or manufacturing process. The same process has to be followed. There's nothing inherently special about it compared to other processes.
Okay, good. Now we move on a little bit to other applications. And we've got a question from whether there are any cases of AM application in processing plants or refineries for quick manufacture of spare parts to minimize unplanned downtime.
So the only one I can think of that's publicly published, but I'm sure there are others, is there was a great example by Siemens for their gas turbine burner nozzle tips, which basically need to be remanufactured. They wear out and they have to be remanufactured. Now, I don't think that's actually done on the site of each, let's say, power generation plant, because the demand, would not generate enough throughput to keep machines busy. But instead, they centralize that, so they basically produce the spare parts centrally and then distribute them to their customers for that purpose. So it is used in that kind of application, but perhaps not as you might imagine, as having a machine on the, at the plant just waiting in case something goes wrong. But rather today it still seems to make more sense because of the throughput that you might get to centralize that. That's not to say it'll always be like that. Maybe one day we'll have more distributed manufacture using this process.
Okay, good. Now we've got a question about the maximum size or envelope of a part that can be feasibly made up in one piece.
So that largely depends, if you'll pardon the pun, on which process we talk about. So for powder bed fusion, where you're getting the resolution that we're looking at there, then there are a few large machines, so specials, which have build chambers up to about 1 meter tall and about 400 millimeters by 400 millimeters in footprint. And you could build a part that size in powder bed fusion. Whether that's economical is another question. So that might be economical in very specific cases. That's why those machines exist. But that doesn't necessarily mean that that's always going to be the best approach compared to an assembly. If you talk about directed energy deposition, then parts many meters in length can be built, but they require some kind of finished machining all over. The biggest advantages there are around material waste, particularly for high value materials. So if you're interested in directed energy deposition technologies, Cranfield University have very good resources online in their WAM mat, WAAM-MAT. If you Google that, you should be able to find some really interesting reports and documents that will tell you more about directed energy deposition and what you can do on that large scale.
Okay, good. We have then a question exactly on the opposite side. When manufacturing a cellular geometry with very small wall thickness, about 0.2 millimeter, as you mentioned, what accuracies can be achieved? Are these wall thicknesses achievable across a range of materials, e.g. aluminium alloys, nickel superalloys, or scalmalloy?
So another good question. So when you go to these small thicknesses, essentially what you're doing is you're limited by the single track width that you can reliably print and build up layer by layer without a problem. So it does depend somewhat on the orientation of the feature in the build chamber, and that generally means it's to do with the relative orientation of those thin vein features with respect to other features in the part. So it's not easy to give a simple answer, but provided they're orientated in the best possible orientation for building them, then generally, similar to the surface finish problem, it depends a lot on things like the thermal conductivity, the surface tension of the melt pool, and so on. Generally speaking, with Inconels and steels, you can go thinner, so maybe down to 100, 120 microns. With aluminium, it tends to be thicker, maybe in the range of 300 microns, single wall, titanium somewhere in the middle. Repeatability in terms of that wall width is pretty good. I mean, in absolute terms. So you would see variation, maybe in titanium, you might have 170 micron average wall width, and it might vary between 150 and 190 microns. So maybe a 20 micron profile variation in thickness of those features. There are a lot of sensitivities to distortion and things like that. So it's not a trivial exercise, but you can make features that small repeatably.
Okay, good. We are coming towards the end. We've got a couple more questions, so maybe we can just try and provide a very quick answer to the questions we've got queued up, and then we will need to finish this one here. So we've got another question on the status on large-scale, high-deposition rate additive manufacturing technologies.
So what I would say is, I mean, use the internet to look, but it's very, I'd say they're reasonably advanced. One thing to look for is what Norsk Titanium are doing with Boeing. That's very interesting, certifying directed energy deposition parts. Again, non-critical parts, but titanium parts for civil aircraft. I think that's quite an interesting development, and there's an awful lot going on in that space. So yeah, expect to see more in the coming years.
Okay, thanks. Then we've got a question whether you can actually color parts with blended powders? Because in the presentation, I think it only had the raw material colors.
To be honest with you, we've never tried it. My guess would be the best approach to color these parts is anodizing, oxidation colors basically, which you can do typically with things like titanium alloys, aluminium alloys. You can anodize for color. But in terms of adding a dye or something with the metals, that's not practical because the dyes, I'm just guessing here, but the dyes would almost certainly be destroyed at the temperatures that you're melting. So generally speaking, if we need colored parts, we're applying standard surface treatments afterwards, whether it's anodizing or painting and so on.
Okay, good. Few more questions. Whether additive manufacturing can be implemented in dentistry, completely different topic.
Yes, but a very good area for application of additive manufacturing. So it's been applied very successfully in dentistry already. It was one of the early adopters of additive manufacturing for things like dental crowns, bridges, and so on. So if you're interested in that area, my suggestion would be to have a chat with Renishaw, someone like that. So Renishaw produce AM machines in the UK, and I'm aware that they've done an awful lot on dentistry applications in the past. So hopefully there's some information on their website, and if not, I'm sure you can get in touch with their salespeople. Would be more than happy to speak to you.
Okay, good. We've got another interesting question, whether there are any examples of additive manufacturing being used to replace parts that have been made out of carbon fiber in the past.
Interesting. That is a good question. I don't know the answer to it. I'm going to admit that. I can't think of one off the top of my head. In theory, I guess the corrosion resistance properties of some of the alloys you can process and being able to go thin enough, maybe you could compete with carbon on some applications. There are also additive manufacturing of at least short fiber reinforced composites is something that is relatively mature now. So very short fiber. It won't achieve the same performance as a classic laminated part though. So you're generally looking at things where you'd replace an injection molded part or something like that.
Okay, good. We've got two more questions. One is whether it's possible to introduce another material into a section of a finished part, so basically to combine two different materials.
So in principle, with directed energy deposition, as long as you've got access and the two parts are metallurgically compatible, you can do it. I've seen some interesting examples of depositing copper onto steel, for example, to improve thermal conductivity. And that's something that if you go and have a look at what the guys making rocket motors with AM out in the US mainly are doing, there are some really interesting applications there. You know, Inconel thrusters with copper exteriors with done in 2 steps with machine cooling channels. It's amazing stuff. So it's worth having a search.
Very good. And we've got a question to repeat the web address for the online application again, because I think that was missed.
So it's www.imechepert.de.
Okay, and I think people can re-listen to the webinar and hopefully get the address from there. Otherwise, if you let us know, we can reply to that. I think that brings us to the end of our question and answer session. Many thanks, John, for answering all of the questions we had. And I hope the audience enjoyed the webinar as much as I did. And we all learned something out of it. So many thanks for taking the time today to give that webinar.
Thanks for all your questions. That was really great. Cheers.